Okay, we're starting a new lecture topic, and it is on memory allocation. We're going to look at dynamic memory allocation and static memory allocation. So this is page 1, obviously. And section 1, we're going to start with dynamic allocation. The word memory is implied there. So dynamic, when you see that, is talking about something that's happening at runtime. And the functions that we're used to using are malloc and C, or there's actually two other memory allocation functions, calloc for clear alloc and realloc for reallocating something you got with malloc. But anyway, malloc's the main one, and also the new operator in C++. Dynamic memory allocation is convenient, so that's a plus. On the downside, it's non-deterministic. So if you're in a function and you call malloc, the amount of time that it takes to return the memory to you can change between calls, and it may return different memory addresses, obviously, and that can change your program behavior, especially if you're misusing the memory chunks that are being returned. But non-determinism is usually a bad thing in a real-time operating system. You want repeatable behavior. The other issue is that malloc can fail, and if it does fail, it returns null. So it's good when you call malloc to actually check that the address you get back is not null. And we are going to look at the glibc implementation of malloc. That's going to be our case study, I guess you could call it. And glibc is the GNU standard C standard library, and it includes a lot of functions, and it's all the code for it is posted on GitHub. So let me just take you there and show you. Okay, so this is the GitHub page for malloc. So if you look just near the top on the left here, the repo is glibc, and then under the malloc directory there's malloc.c, and this is a long file. I didn't count the lines. It's probably a couple of thousand, and it's basically the pthreads malloc implementation, which is based in part on Doug Lee's implementation, so Doug Lee was using C++ in the 80s, and the dynamic memory allocation was really slow, so he decided to write his own memory allocator, and that became the basis for what is now used in the GNU libc implementation. And there is a link to Doug Lee's implementation, Doug Lee's description of how malloc works here. And it's a bit simpler than reading the source code, so if you're interested, you could go look that up. Some of my discussion will be based on Doug Lee's webpage, but most of it will be based on this documentation, which is actually really good. Okay, back to our notes. So malloc allocates out of the heap. So there's this region of memory that it uses to satisfy calls from the application for memory. And the heap starts empty. This is in the glibc version. I think in the version that we use in the lab, it actually starts at a set size and it stays that size. But with glibc, it actually grows through calls to the operating system. So it starts empty, and it makes system calls In the case of Linux, that would be the S break for set break call to increase the heap size. And what it does is it moves what's called the program break. So it moves the program break, which marks this starts at the end of the data segment. So let me draw you two diagrams here. So on the left here we have the before picture, or the starting picture, where the heap is empty. And so we've got the text segment, we've got the data segment, and the program break starts here. And if that's the case, then the heap size equals 0. And to be complete, we should show the stack down at the bottom of the address space. So when we make a call, well, actually when Malloc makes a call to sbreak, then it's adding an increment to the address of the program break, and the size of that increment is usually something like 64 kilobytes or more, because making system calls is expensive in terms of the amount of time that it takes. So there's our text segment, our data segment, and now we have created some space for our heap, and we have our stack down at the bottom here. So now the program break is right here. So system calls are expensive, and so the implication is that Malloc requests large sbreak implements. So 64 kibibytes, I almost said kilobytes, 64 kibibytes or more, depending on the implementation. And then it breaks that chunk of memory that it gets. I shouldn't use the word chunk because that means something in Malloc, but it breaks that region of memory into smaller chunks that it then doles out and calls to Malloc.